I want to thank the organisers for inviting me to give a summary of the work we've been doing at the group of Jens Biegert at Icpeac in Barcelona, where we've been looking at extracting molecular structure using a method called laser-induced electron diffraction. And specifically, we want to extend the method that has been shown to work for diatomics already. We want to extend it to polyatomic molecules, and also we want to apply it to aligned and anti-aligned molecules as well. So I had a motivational slide set up, as you can see in the background, but after I heard the plenary talk of Professor Zival yesterday, I thought that a quote from him more accurately describes the situation that we find ourselves in. And the quote was, "The first step is to find structure, but in the end we are all after dynamics." And this is exactly the situation that we find ourselves in with laser-induced electron diffraction. We want to be able to extract molecular structure such as bond lengths and bond angles, but in the end we're really wanting to use the intrinsic temporal properties of strong field ionization to extract molecular dynamics at a resolution that's either very hard or impossible with other techniques. Okay, so what is laser-induced electron diffraction? Well, it's basically a combination of ultra-fast electron diffraction, which has been typically used to measure molecular dynamics at about 100 femtoseconds or greater. It's a combination of that with strong field ionization. Now, strong field ionization can be described classically using the rescattering model developed in the 90s by Paul Corkum and others. And I'll describe that now. First of all, you have ionization, which after the interaction of a molecule or an atom with a strong laser field. An electron can tunnel ionize. And after the ionization event, it then propagates in the field and gains some energy. And the amount of energy it gains is proportional to the driving wavelength squared. So if you want high energy electrons, it's very beneficial to use longer driving wavelengths. This is important to our methodology. And then as the electron propagates in the field, it can come back and return to the molecule or atom. And provided it's propagated far enough away from the target, then you can treat it as a plane wave upon return. And if that's the case, if you have a plane wave electron coming back and scattering off a target, then it's very similar to the ultrafast or conventional electron diffraction technique, where molecular structure is encoded in the diffracted electron map or electron momentum distribution. Okay, so just quickly before I go into our results, I just wanted to highlight our unique experimental apparatus, which is one of only a couple in the world. And so we have a reaction microscope, which has been covered a little bit in this conference already, but the main points are that it is able to detect the full momentum distribution of a strong field ionization interaction, so in full coincidence in 3D. And so you can have an ion that you detect, and you can know for sure what electrons correspond to that ion only. Now, this is a critical factor in laser-induced electron diffraction of polyatomic molecules. I don't have time to go into it today, how critical it is, but if anyone's interested in the question time, you can ask me about that. I have some backup slides. And we combine a reaction microscope with our high repetition rate mid-IR source, which has two outputs that are relevant to this talk. One at 1.7 micron, which we use to impulsively align our molecules, and one at 3.1 micron, which we use use for the laser-induced electron diffraction method. Both of these can ionize, or can reach intensities that can ionize atoms and molecules, and it's a really very stable system. We can run it for days on end with very small changes to the laser parameters. Okay, so while it is very similar, laser-induced electron diffraction is similar in some ways to ultrafast electron diffraction, it does occur with a strong field being present. And so you need to take that strong field into account. And a clever way of doing that was developed by the group of Professor Chi-Dong Lin at Kansas State University. They developed this quantitative rescattering model, which you can use to describe a measured electron momentum distribution as purely the product of a field-dependent electron wave packet and a field-free differential cross-section. And so what you see on the bottom left here is actually measured, experimentally measured momentum distribution after the ionization of xenon with our 3 micron source. And what you actually, if that pointer doesn't, there we go. You see 3 circles here of different radius and of different origin, or their centers are displaced from the origin by different amounts. And so each of these circles represents scattering of an electron with a different momentum, so a different incident momentum upon scattering. The radius is purely the electron momentum upon scattering, and the shift, this AR here, is the vector potential at the time of rescattering. And both of these values can be calculated using the rescattering model I showed earlier. And so you can extract field-free differential cross-sections by simply scanning around these circles, around the circumference of these circles, and counting the amount of electrons you have as a function of the scattering angle. And so in this case, we've done it for xenon, and we show our results here. And they're shown against against NIST calculations that are provided on their website, which are known to be accurate. And so we can see a very good agreement between our results and those calculations over a large angular range between about 50 and 180 degrees. And so we're sure that the technique works, and now we want to apply it to molecules and try and get molecular structure from the diffraction patterns. Just to highlight, this work here has been published recently in the past couple of weeks in PRX, and I encourage you to read it. Okay, so what molecule are we interested in? Well, we want to go to larger molecules and diatomics, and so we chose acetylene, and it's actually a very good molecule to investigate because it's very well known. The bond links of the cation and the neutral are known accurately, and it's easily alignable, as has been shown in the literature a number of times. It's linear and symmetric, so orientation is not necessary. But it is polyatomic. It's got 2 carbons and 2 hydrogen atoms. And something that's of interest to me in particular is that it's an organic molecule, and as such should feature a number of interesting dynamics associated with the proton, such as deprotonation and also isomerization. And these are things we would like to study in the future. Okay, so we can extract these differential cross-sections from both the atomic and the molecular case. But in the molecular case, how do we use that to extract bond lengths? And so there's a factor here called the molecular contrast factor that was defined by Cheadon and his colleagues. And it's simply the comparison of the experimentally measured molecular DCS to the atomic DCS, or incoherent summation of atomic DCS as a constituent atoms in the molecule. And when you put your experimental data into that formula and you calculate your molecular contrast factor, you get something like this, which looks a bit like an interference pattern. It has minima and maxima and 0 crossings. And these are the features that are sensitive to the molecular structure. And so you can perform a fit-in routine where you vary the carbon-carbon and the carbon-hydrogen bond, and you calculate the molecular contrast factors you would expect for those bond lengths, and you can perform the fit. And you get, in this particular case, we find carbon-carbon bond length of 1.21 angstroms and a carbon-hydrogen bond of 1.07 angstroms, which are both within a few percent accurate with the expected values. And so I wanted to point out the sensitivity of the technique. And so if you construct a molecule with these bonds that we've just found, and then you contract or you expand the molecule, you can then find the molecular contrast factors that you would expect from those different molecular geometries. And here I plot those different molecular contrast factors, and you can see that they shift, and we can easily resolve the differences between them. So we're very confident we're getting molecular structure at the 10% or less level. But of course, this strong field ionization creates a broadband wave packet, and so you're not just getting interaction or a scattering of one particular energy, you're getting a large range of electron energies. And so we performed the fit-in routine that I just showed for a whole range of energies for both aligned and anti-aligned molecules. And I'll just point out now that I don't have time to go into the alignment aspects of this study, but if anyone's interested, again, please ask me at the end of the talk. And so for a number of electron energies between 50 and 100 eV, we found the CC, which is the top panel, and the CH bonds. And so the dashed lines are the expected values, and you can see that our experimental results agree quite well with the expected values over a range of energies. And so what we do is we do a horizontal line of best fit through our data, and these are the numbers or the bond links shown in each panel. And so we're getting values that are very close to the expected values with errors on the percent level and accuracies on the 5 picometer or less level. And so we've just published these results in Nature Communications in the past couple of weeks. And again, I encourage you to read that paper for more details. So as has been discussed in this conference, the broadband wave packet that you do get in strong field ionization is also chirped. And so this means that each electron energy has a different return time. And so you can map each of these electron energies I show up here to a different time after ionization. And so using this energy to time mapping, you can associate, or you can create an axis here of rescattering time. And so you can see in this particular case, using these electron energies, we have a window around about 1 femtosecond wide, about 8 femtoseconds after the ionization event, that we can probe the molecular structure. In this particular case, we're looking at the cation of the ground state of the cation, and so we don't believe there should be any significant dynamics, and indeed it doesn't look like there is. But of course, we're using a coincidence detection measurement device, and so we don't have to look at the cation only. We can look at different fragmentation channels or multiple ionization or something else. And so that's what I want to talk about for this last slide. Here we show, on the left-hand side, we show the results for 50 EV electrons interacting with the cation. And these molecular contrast factors result in bond links that are very close, or within 10% of the expected values that are shown on the bottom. But then we can also get the electrons from the dissociation channel of the dication into H+ and C2H+. And the blue curve here, the blue corresponds to aligned molecules, the red corresponds to anti-aligned molecules. So in the aligned case, this deprotonation gives bond lengths of the CH and the CC that are very close to the equilibrium bond lengths. And so we think that we're imaging a slow deprotonation channel, maybe from a metastable state or something like that. But something interesting happens when we look at anti-aligned molecules. In that case, we see a very large lengthening of the CH bond length to almost 2 angstroms from around about 1 angstrom. So almost a 1 angstrom increase in size. And so we hope, or we think, that we're seeing some type of fast deprotonation, and we're imaging it within 10 femtoseconds after ionization. Now, I want to point out that these are very preliminary results. We have ideas about what might be happening here, what states we're populating, and the dynamics that are occurring, but we don't know for sure just yet. And so if anyone in the audience is interested in discussing this or giving ideas and things like that, then myself and my student, Benjamin Volta, is in the audience. We're both very interested in discussing these things with everyone. And so the question we're currently asking ourselves is, of course, are we imaging alignment-dependent deprotonation? So are we controlling the speed of this deprotonation process by changing the molecular alignment? And so with that, I want to acknowledge the people involved in this work, specifically Ben Volta, who's in the audience, and my other colleagues at ICFO, and of course my boss, Jens Biegert. And then we have some theorist collaborators at Kansas State University that helped us a lot, and a number of people in Germany who are scattered around Germany these days who helped with the experimental apparatus. And with that, I'll leave you with my summary and my outlook. So thank you for your attention.